Hello, welcome to Advanced Composites. Today is the fourth day of the ongoing week, which is the fifth week of this course. And what we have discussed over this week is we have started with force equilibrium equations, and we developed these three of these equations for x, y and z direction. And then yesterday we developed the three moment equilibrium equations. And what we found that while developing the moment equilibrium equation for the for the third axis, that is z axis, we found that the fact that tau xy equals tau yx, that means nxy equals nyx, and that implies directly that the sixth equilibrium equation will be identically satisfied. So, effectively we have only 5 equilibrium equations, mutually independent equations, and we will again rewrite them and process them further. So, what are these equations? Del nx over del x plus del nxy over del y equals 0. This is for the x equilibrium for forces, del nxy, and now because nxy is equal to nyx, I am just going to write it like that, del x plus del ny over del y equals 0. This is the second force equilibrium equation. The third equilibrium equation is del qx over del x plus del qy over del y plus q equals 0. And then we have the moment equilibrium equations, del mx over del x plus del mxy over del y minus qy, no, qx equals 0, and finally we have del mxy over del x plus del my over del y minus qy equals 0. So, these are the 5 independent equilibrium equations. All of them are partial differential equations in n and m, moment resultant and force resultants. And what is their order? Their order is, they are first order PDEs, first order partial differential equations. And if we solve these equations, we will get the solutions for nx, nxy, ny, mx, my and qx and qy. So, these are the equations. Now, what we will do is we will combine the last 3 equations into one single equation, because that makes things a little bit easier to handle mathematically. So, we will number these. So, this is A, B, C, D, E. So, we know that from D we know that qx equals del mx over del x plus del mxy over del y. Okay. So, if we partially differentiate this equation in x, we get del qx over del x is equal to second derivative of mx with respect to x plus del 2 mxy over del x del y. So, let us call this equation f, and then likewise from E, what do we have? We know that qy equals del mxy over del x plus del my over del y, and if we partially differentiate this whole equation with respect to y, then we get del qy over del y equals cross derivative of mxy with respect to x and y plus del 2 my over del y square. So, we call this equation G. Okay. So, we see that this is del qx over del x, and which is same as this, and in equation C the second term is partial derivative of qy with respect to y, and that is there in equation G. So, we put f g in C, and finally what we get is del 2 mx over del x square plus twice of del 2 mx y over del x del y plus del 2 my over del y square plus q equals 0. So, this is the other equation. So, we have H. So, I can use these 5 equations A, B, C, D and E, or I can use these 3 equations. Okay, I am sorry, is equal to q. So, did I write q in the other one? So, actually q is on the left side, 0. So, here what we have done is we have reduced the number of differential equations from 5 to 3, but whenever you do such types of reductions, what ends up happening is that you raise the order. So, we have reduced the number of differential equations, but we have increased the order of the third differential equation. So, earlier it was just first order, now this is a second order differential equation. Okay. So, this is, so if we solve these equations, we can find out what is, so at every point, so what is the point? So, the aim is to solve these partial differential equations. Once you solve these partial differential equations, we get values of nx, ny, nxy, and what else? mx, my, mxy at all points in plate. Okay. So, if we are able to solve these partial differential equations, then we will be able to calculate nxy, ny, nxy at all the points in the plate. Once we do that, then as a next step, what we can do is calculate epsilon naught and k naught curvatures and mid-plane strains and mid-plane curvatures at all points in plate, and once we are able to do that, then what do we get out of it? calculate strains at strains at points of interest and once we know the strains at different in different layers, because now if we know epsilon naught and k naught, then using the relation between epsilon naught and k naught we can calculate strains at different layers at different points. So, then we can calculate stresses in the plate right. We can calculate stresses by using Q bar matrix and epsilon matrix for the kth layer. Okay. And once we know that, we can predict the failure of the plate. So, we can know whether our plate is strong enough or not. So, this is the overall process. You start with partial differential equations, solve the partial differential equation, you get nx, ny, nxy, mx, my, mxy. Once you have knowledge about these moment and force resultants, using these force and moment resultants you compute mid-plane strains and mid-plane curvatures at different points in the plate, or actually at all the possible locations. Once you have that, then you can at every cross section you can calculate how strain is varying along the thickness of the plate, and that will help you calculate stresses in each layer of the plate using, because then you can find epsilon k and q bar k, and you can calculate stresses in each layer of the plate, and then you can transform these stresses to LT plane, right. So, you can find out sigma L, sigma T and tau LT, and then using the work energy this maximum work criteria or maximum stress criteria or maximum strain criteria, you can compute whether the plate is going to fail, and if it fails which particular layer is going to fail, and so on and so forth. So, this is the overall process through which you can design composite laminated plates. In this entire process, there is one thing which we have not discussed till so far, that whenever we solve these equations, whenever a differential equation is solved, then once we solve these equations, we will essentially, what does that mean? When we solve a differential equation, this is a differential equation, we integrate it, right, we integrate it, and whenever we integrate a partial differential equation, we get some functions. So, when we solve this, we will get a function from here, another function from second equation, and the third equation is a second order differential equation. So, we have to integrate it twice. So, we will get two functions from the third equation. So, and these functions are unknown. So, we will have to figure out their values, and the way we figure out their values is that if we have a plate, then on each edge there will be some boundary conditions, and if we know these boundary conditions, then if we know these boundary conditions, then in terms of these boundary conditions we can figure out or calculate the integration constants or integration functions which are gotten because of integrating these things. And so, the boundary conditions will help us determine integration functions. So, we have to know what kind of boundary conditions are existing on every single edge of the plate. So, in the next class, and this requires some detailed discussion. So, in the next class we will actually discuss what kind of boundary conditions are required, what kind of boundary conditions we should know, and we have to specify so that we can determine these integration functions. So, that is what we plan to discuss tomorrow. So, that is pretty much all for today, and I look forward to seeing you tomorrow at the same time. Thank you.